Okay, hi everyone. So today I will be continuing on chapter 4, which is the analysis of inorganic analytes in terms of spectroscopy based methods for inductively coupled optical emission spectroscopy and then inductively coupled mass spectrometry, ICP-MS. So this instruments are going to be looking at into the emission spectroscopy. Before this, during chapter 3, we have looked into the atomic absorption spectroscopy, where you have looked into flame atomic absorption, graphite furnace atomic absorption, and then we've looked into a very specific atomic absorption spectroscopy, which was hydride generation, and then the cold vapor atomic absorption, which is very specific towards the analysis of mercury. Okay. All right, so basically that is atomic absorption. Now we are going to look at the emission. Okay, emission. So when I say emission, so you straight away would think that so for emission to happen, your atom or your analytes need to be in the excited state, and then it goes back down to the ground state by releasing a characteristic electromagnetic wave which will be detected by the detector. That's how emission happens. Before this, we have looked into absorption, where the absorption, the wavelength or the electromagnetic radiation would be would be provided by a source. Okay, so now emission, you need to be able to think that on what is the transition. Okay, so atomic absorption would happen from the ground state to the excited state, and then you measure the transmittance. But for emission, from the excited state to the lower state or ground state, where it will emit and a characteristic electromagnetic wave. All right. So moving on, so now we are going to look at into what is flame atomic emission spectroscopy, and then the theory of ICP-OES, the instrumentations, and then the theory and instrumentation of ICP-MS. All right. So atomic emission spectroscopy. So the theory, the principle is what I have explained before. All right, so AES uses measurements of optical emission from excited atoms to determine the analyte concentration. So now as what I've mentioned before, it uses the emission of electromagnetic wave from the analyte itself. So the analyte atoms, which is in the solution, which were aspirated into the excited region, emit radiation when it revert back to the lower levels, or we call it ground level. So the advantage of atomic emission over atomic absorption is that all of the atoms would be excited simultaneously, hence it will be detected simultaneously by the detector. Okay, we'll be looking at into this later on, but this is the advantage of AES over AAS. Okay, because in AAS, the excitation would be happen for individual analytes. But for AES, all of the atoms in the sample are excited and detected simultaneously. All right. By looking at this illustration, you would see that AAS have a source of radiation. So this source, before this, for example, we've looked into the hollow cathode lamp. So if you want to analyze copper inside your flame, then you would need to have a copper hollow cathode lamp, because the radiation would be emitted by the source and be absorbed by the copper metal inside the sample, and then it will be detected by detector. But for AES, atomic emission, the flame itself would act as the source of excitation. So it will excite your analytes inside your flame here. Then your analyte itself would act as the source of radiation, because the emission would comes from the analyte itself, not from the source. So that's why in AES, we don't have any source here as compared to AAS. We don't have any source because the source of radiation would come from your analyte, because your analyte would emit electromagnetic wave. The flame here would act as a source of excitation. So it will excite your analyte simultaneously. So the process of excitation, and then goes back to ground level, emit radiation, then there goes your emission wave, which is a very characteristic toward each elements. Okay, so if there is question of how are you going to differentiate between AES and AAS, so this is how you will answer. Okay, all right. So this is an example of AES spectrum. So as you can see here, all of those metals are detected simultaneously. Okay. So type of atomic emission. Now we have three atomic emission, which is a simpler one, which is a flame photometer. And then we continue with ICP-OES and then ICP-MS. Okay. All right. So flame photometer. So it will be using flame for atomization. And then we have an optical filter, and then it just emit. All right. So flame photometer. Flame photometer, all of the atoms are excited in the higher energy in the flame. So all of the atom would be aspirated into the flame. So the flame itself will atomize and excite your analytes. So this excitation would be would create would make your atoms to become the excited level. So at the excited level, it is not stable. It will go back down to the ground level. So this from excited going back to the ground level would emit a characteristic electromagnetic wave, which will be detected by the detector. So similar optical system as UV-Vis, but the source of radiation is provided by the analyte itself. So basically, when we say that the source of radiation is provided by the analyte itself, so we don't need any source now. So the flame would act as your uh, excitation medium lah, kita panggil excitation medium, and then your source of radiation, your source of emission would come from the analyte itself due to the relaxation going back down from the excited to the lower level. So this flame photometer is very cheap, simple, has flame stability, and the temperature is not that high. All right. So now we are going to look at okay. So basically, this is the example of a flame photometer. All right. So now we are going to look at inductively coupled plasma optical emission spectrometry. It is quite a mouthful, but don't worry. So basically, what you need to know here, there are two keywords inside this, which is the first one is plasma, and the second one is, as what we have learned before, emission. So now you need to know plasma and how it emits. Okay. So it carries out the same principle as the plasma would be the medium for your sample to be atomized, to be ionized, and then act as a medium for excitation. So your analyte will be excited. So your analyte will be the source of radiation, where it will emit a characteristic emission wavelength for it to be detected by a detector. It is still the same, but now it uses plasma as compared to flame photometer uses flame. Okay. So now this is example of ICP-OES instrument, okay, is quite big. All right, so now, as I mentioned before, so you need to know what is plasma actually. So plasma is, in a nutshell, plasma is like a flame, okay? But a plasma is a stream of highly ionized gas containing electrons and positive ions. It is electrically conductive, and it is affected by a magnetic field. So when if there is any question, or if there is some people would ask you, what is plasma actually? So this is how you answer plasma. Plasma is a stream of highly ionized gas. So it is not flame. Flame is just api. But now it is a stream of highly ionized gas containing electrons and positive ions. Okay? All right. So basically, it appears like a flame, but it's not a flame. Okay? All right. So basically it has a very macam cylindrical ovally shape. Okay, so it looks like flame. So basically your sample, if you can imagine that your sample would be coming from down here, it is aspirated into the flame, which it will be excited into in the analytical zone lah, which is about 5,000 until 8,000 Kelvin. Okay, so the induction zone is quite high. It's at 10,000 Kelvin, where the dissolution, evaporation, dissociation, or even excitation would be happening inside the flame itself. Okay, all right. So the theory of ICP-OES. So it uses inductively coupled plasma, as I mentioned before, at a very high temperature, okay, around 6,000 Kelvin to 10,000 Kelvin, which the plasma would be able to dissolve it, vaporize, excite, and ionize atoms. The intensity of the light emitted would be proportional to the amount of element in the sample. So the higher the intensity means that the concentration or the amount of the element would be high as well. Okay, it's directly proportional. So ICP is ideally suited to for a rapid multi-element analysis. So this is what we've mentioned before. AES over AAS. So AES, you will be able to excite, and then you will be able to detect all of the elements simultaneously. It provides high sample throughput with a wide calibration range, low background and low detection limits for many of the elements. So usually it be using for it can be used for major or minor, but it is usually used for trace analysis with a few interferences. Okay. All right. So the process in ICP-OES, I think that this process is quite similar to the one that you have seen inside the atomic absorption. So we will have a removal of solvent, which is dissolution, where the solution will become solid, and then we have a vaporization, the solid will become gas, and then atomization, excitation, emission, and then ionization. All right. So, what are the advantages of this ICP over flame? So now we are comparing emission method in flame and emission method in ICP-OES. So, ICP-OES would be able to offer a lower inter-element interferences because it is conducted at a very high temperature. The spectral interferences is being controlled by the instrument design and also by the software. All right. So with a single set of condition signals for dozen of elements can be recorded simultaneously. It has a lower LOD. LOD means a limit of detection. So means that is very suitable for trace analysis. All right. So the detection limit is moderate to excellent to a much more low ppm lah, part per million. And it is very fast. The only disadvantages of ICP OES over flame AES is that it is more complicated and expensive to run because you need to create the plasma, and then it requires a higher degree of operator skill. Okay. All right. So the ICP-OS instrumentation is as what I've shown here. So you would see an RF generator, continue to torch, spectrometer of the optics, and then detector, and then lastly the computer. So we are going to look at it but one by one. All right. So this is the schematic diagram of ICP-OES. So ICP and the sample introduction would be around here. So the nebulizer. Okay, this is your sample. The sample would be, we have a pump here, which we will be pump into the nebulizer lah. So, and then it will be into a spray chamber into the ICP torch, where all of this, the atomization process that we have looked before would be happening inside the plasma, sorry, the plasma. So this the radio frequency generator, where it is located below the plasma, where it is used to generate the plasma. And then the emission from the flame would be detected by the spectrometer, and then we have a PMT, photomultiplier tube here, all right, for it to be processed by the computer later on. All right, so basically this is more or less the schematic diagram of ICP-OES. It is just that it has a couple of addition as compared to a simple flame photometer. All right. So now we are going to look at the first thing is the nebulizers. So the nebulizers is that is for it to convert the liquid, your sample, which is need to be in liquid form. It needs to convert the liquid into aerosol particles that can be transported into the plasma by argon gas. So type of nebulizers, we have 2, 4, 6, 6 type of nebulizers. Okay, so all of these nebulizers have its own characteristic, but I don't think that we are going to look into each in depth. So it's just sufficient for you to just know the types of nebulizers available for ICP-OES. So concentric nebulizers, micro concentric nebulizers, okay? So all of the nebulizers, the functions are going to convert the liquid, which is your analytes, into an aerosol particle so it can be delivered or carried into the plasma. All right. So the spray chamber, which is to remove large droplets from the aerosol. So after it's been converted into the aerosols, some aerosols might have a large droplets. So this is to remove large droplets into the aerosols, which smooth out pulses that occur during nebulization. So allow droplets to have a diameter about 10 micrometer or smaller lah, to pass into the plasma. Okay, 95 to 99% of the sample is drained into the waste container. Right. So that is a spray chamber. So spray chamber here also you can see there is a conical type spray chamber and then Scott type spray chamber. Okay. And then we have the radio frequency generator, or we call it RF generator. It provides power for the generation of plasma. So sustain the plasma discharge about 700 to 1500 watts. Okay, so the usual operation of ICP-OES is at the frequency of 27.12 and 40.68 megahertz. So this is just for you to, for your general knowledge only. So, but you need to know the functions of each. What is the function of nebulizer? What is the function of spray chamber? What is the function of radio frequency generator? All right. So now we are going to look at the plasma torch. Okay, so there is a lot of flows here: plasma flow, auxiliary flow, and the nebulizer flow, where the nebulizer flow would be carrying your analytes into the plasma torch. Okay, so the detection in ICP-OES, usually the detection is using a charge coupled device. So it is an integrated circuit chip where you can see that your radiation would your radiation would apa ya kita kata would be detected by this integrated circuit chip, where it contains an array of capacitors that store the charge when the light creates electron hole pairs. Okay, so the accumulated charge is read out by at a given interval later on. So each wavelength is detected at a different spot. Okay, so uh, when your radiation bombard this charge coupled CCD, so each of the radiation would have a specific site on the CCD. So when you have a specific site, it can create a simultaneous detection. Okay, because each wavelength is detected at a different spot. So this is how a CCD or even your radiation would be, your emission from your sample would be detected simultaneously. Okay, all right. So, all right. So let's recap on the different types of schematic diagram here. Okay, this is not schematic diagram, but it's just an illustration of showing you the atomic absorption, atomic emission, and then atomic mass spectrometry after this. Okay, so as what we have looked at before, atomic absorption, we need to have a source of light here, and the absorption would happen in the flame, and then the transmittance would be uh, converged by the monochromator into the detector. But for atomic emission, the excitation would happen in the plasma or flame, and the emission or the source of radiation would comes from the analyte itself, and then it will go into the monochromator, which will be detected by the CCD. All right. For atomic mass spectrometry, which we will be looking after, which we will looking it after this. So when we look at atomic mass spectrometry, it is the same as atomic emission, but the detection is by the mass of the element. Okay, so it will be separated into mass of each of the elements. So because each of the elements have its own mass, so it will be detected in terms of mass lah, as compared to atomic emission, which will be detected as the emission. Okay. All right, we will look at after this. So the application of ICP-OES. What is the application of ICP-OES? It has a lot of application, usually in terms of agriculture, when you want to look into the nutrient level in soils, whether the fertilizers used are sufficient enough to make sure that you have a sustainable production of crops. Even in terms of environmental, if you want to look at into a water sample which has been polluted with a lot of heavy metals, so if you are using AAS, you need to measure it. If you have if you predict that there is going to be 10 um, metals that has been polluting the water sample, then you need to do 10 analysis. So that's why you need it is wise for you to submit it to for ICP-OES analysis. So it be all of that will be detected much more faster and simultaneously. All right. So there are other application also in terms of geochemicals, where you would be able to analyze the minerals in the rocks. Also in terms of the petrochemicals, analyze gasoline, oils, coal, or even plastics. Okay. So, all right. So, inductively coupled plasma mass spectrometry. So, this is what I've mentioned before. So, it uses plasma also as the atomization. And then we have a mass filter here. Okay, mass filter here. And then an ion detector later on. So, there's a difference in terms of ICP-MS and ICP-OES. Because for ICP-OES, let's look back. For ICP-OES, where is it actually? So plasma for atomization, but it uses optics and then emit. All right. But for ICP-MS, it uses mass filter and then ion detector. All right. Let's look at it. All right, so this atomic mass spectrometry, as mentioned before, this is an example of apa ICP-MS instrument. So it's quite large actually because you only have those quadruple mass filter and then the ion detector. All right, so ICP-MS is a technique to determine elements using mass spectrometry from the ions generated by the ICP. All right, so when you have looked into the atomization process, towards the end you have ionization, isn't it? Okay, it will be happening inside the flame due to the high temperature. It will be until ionization. Okay, so as compared to AAS, ionization is not apa? Is not favorable. It's not desirable to happen. Okay, but for MS, for ICP-MS, it using the it is a technique to determine the elements using mass spectrometry from the ions generated by the ICP. So this mass spectrometry is a measurement of the mass of the individual atoms of a material. Okay, so now we are going to look at into the instrumentation part. Instrumentation. All right. So basically we have a seven sections where I think the most important thing it is the 3, 4, and 5, even 6. Okay, 3, 4, 5, 6 is something that is quite different from the ICP OES. All right. So basically, this is the schematic diagram of ICP-MS. So for the spray chamber, even from the sample aspiration into the torch, even for the radio frequency generator, RF supply here is quite the same. Okay, so it's quite the same as ICP OES. It is just that after the emission from this plasma, it will be conducted into the ion lens. All right. So the ionization would happen inside the ionization would happen inside the flame. So the ions will be carried into the ion lens, and then the ions will be separated in this mass filter, or we can call it quadruple filter, where the ion or the electron would be detected by the electron multiplier and being processed by the computer. So now, when we talk about ICP-MS, it is mainly about the ions itself, right? Okay, so now when this is the example of a spectrum of an ICP-MS spectrum. Okay, so looked at here Li, lithium plus, C plus, or even Ag plus. So all of these are ions that has been generated inside the flame itself. All right. As compared to before this, we have been looking into the emission spectroscopy. Now we are look at mass spectrometry or mass spectroscopy lah. So now we mainly solely we are looking at the mass itself. Okay. So the ion source and the extraction system. All right. So harsh plasma environment. So the plasma actually has a very high temperature, and combined with the spectrometer, which has a stringent environmental demands of 0.001 torr at ambient temperature. So this is just for your knowledge only lah. Alright. So the interface is that to get the ions from the ICP, to get the ion from the plasma to the spectrometer where the mass separation will be done, we need to have this interface. Alright. So the ions from the ICP travel through the sample cone orifice and then the schema cone due to difference in pressure. I think that you have an interface here. All right. So the ions, okay, the ions from this ICP, where from the plasma, where the atomization until ionization would happen in that plasma. So the ions will be traveling into the into the, what is it called? Into the mass filter, which is the quadruple, it needs to have an interface which is in this, which is we call sampler cone and then the schema cone. Okay, so uh, the ions would be able to travel through the sampler cone, which is this one, the sampler cone, and then the schema cone. Okay, into the uh, mass filter, which is the quadruple. So the sampler cone is that ions are sampled through a 1 millimeter orifice into a 1 to 3 torr pressure region. So the sampled material are representative of the plasma central channel. Okay, the argon atoms are removed by the vacuum because we have the argon gas inside the plasma. So the argon would be removed by vacuum. We don't want to be able to detect the argon because argon is not a part of the metal that we want to analyze. Okay. And then we continue with the schema cone where the ion beam is further sampled through a second orifice, which is about 0.9 millimeter. Okay, and then we continue it for photon stop and then ion lens assembly before moving on into the quadruple. All right, so what is the function of ion beam actually? Okay, when we looked here, I think that, okay, there is here. All right, so tadi kan when we look into the ICP, so this is the plasma. There is a interface here, which is the sampler cone, and what is the other one? The sampler cone, and then the schema cone. Okay, sampler cone, schema cone, and then moving toward the ion lens. So what is the function of ion lens? So ion lens, it focuses the ions extracted by the interface, the two cones, and then sends them into the quadruple. Using the electric field from specially shaped metal piece, the ions are pushed into the quadruple. All right, so this is from the schema, and then going into the cylinder lens, and then it focuses the ions into the quadruple. All right. So the quadruple mass filter here, it separates one type of element, which is ions in this case, from another. Okay, the electromagnetic field of the quadruple rods allow only one mass to make it through at a time. So usually, when we looked at here, okay, so you would imagine that inside the ICP, okay, let me look at this one. Okay, you would imagine that inside the ICP, inside the plasma, there is all of these ions, and then it moves into the interface where the ions are being are being filtered now, are being filtered, but filtered, even though it is filtered, it is still representative of the central region of the plasma. Is still representative of the sample. All right, so now it focuses into the ion lens, and then now they are in the beginning of the quadruple, at the apa orang kata tu, at the door of the quadruple. Let me see that. Okay, so now the function of the quadruple is that for it to permit only one ion at a time. Okay, one ion at a time, so that there are a lot of ions here that is at the door of the quadruple, but only one detection at a time. Okay, so based on this spectrum, you can see that the first ion that is being let through into the quadruple is the lithium plus. Lithium plus ion, and then continue by the C plus, O plus, Na plus. All right, because it depends on mass now. Okay, so the separation, we can say that the separation of ions would be depending on the mass based on the quadruple, where it only permits one measurement at a time, not all of the ions from the plasma going into the quadruple. Many masses enter, only one makes it out. Okay, so as you can see here, there are a lot of mass here, but only one measurement at a time. Okay, so now we are going to look at the detector. So it counts the number of ions leaving the mass filter, the quadrupole mass filter. Ions leaving the quadrupole will collide with the detector, producing a cascade of electrons, which can be measured by the signal electronics. So, for example, you have 10 lithium ions, so it will be counted as 10 signals, something like that. For example, you have 4Na only, and it's counted as 4Na. Even though it is separated by mass, the quantity of each of the ions also will be quantified by the Dynamo detector. All right. So, example of ICP-MS spectrum. So you can see that basically we can look at the different types of isotopes actually. Okay. For example, this copper 63 and copper 65, you can see that 69% in abundance of all of the copper inside the sample would comes from copper 63, but copper 65 is only 31%. So that's why when we say that even though with mass filter quadrupole, even though it's the same element, it can also detect different kind of isotope because of the mass. Okay, so the application of ICP-MS as what we have looked into ICP-OES also, there's an environmental, clinical, even blood, urine, serum, isotope tracer studies for petrochemical. All right, so these are the application of ICP-MS. You may have read on it. All right, so the difference between ICP-MS and ICP-OES, you can see that uh, apa uh, the compound that can be detected, most of it is the same, most metals and non-metals. But for ICP-OES, most metals and some non-metals. In terms of detection limit for ICP-MS, it has much more lower detection limit at PPT, part per trillion. Advantages is for ICP-MS is rapid, same as ICP-OES. Okay, so disadvantages of ICP-MS is that limited total dissolved solids tolerance. So because for ICP-MS, due to the function of it being using from only mass, so and also you need to be able to have a clean sample actually, right? So for ICP-OES, the complex interferences would be reducing the sensitivity as compared. AAS is much more, or AES flame photometer also is much more rugged in terms of whenever it comes from for complex interferences lah. All right. So the detection limit also, when you can see that, for example, ferrum here for flame AAS, the detection limit for ferrum is at 5 ppb, but for ICP-MS in terms of ferrum, it can goes down to 0.05 ppb. So this is the recap of whatever that we have learned before for atomic absorption, atomic emission, and atomic mass spectrometry. So this is also the summary of atomic absorption and atomic emission. All right. So I think this is the last slides for this topic. So decision criterions in what to choose. So when you are being given a sample, so you need to figure it out on what to choose actually, which instrument to choose. Okay, you want to use atomic absorption ke, you want to use ICP-MS ke, it depends on the criteria. Okay, ICP-MS, if you look here, most expensive but best because it covers all elements, including hydrides, including mercury also. So it is a fast multi-element analysis, but the price range is quite high. Or even you would go to the much more lower, which is a flip AAS, fast, but it's just per sample single analysis. So it depends on you actually. It depends on the criteria. It depends on the analyte itself actually also. But if you just go straight to ICP-MS for all of those things, then you don't have any balance in terms of the optimization of whether you need to go to high end with a higher price, or you can also save some money when you go to much more lower instrument with a sufficient decent detection limit and sufficient time of analysis. Even so, it's a good range of analyte to be detected. All right. So you may look into this decision criteria, and this is very important for you to be able to select the best instrument for the sample that have been given to you. All right. So okay, this is also the another representation of decision criteria. All right. So you may look into it. All right. So this is the one I've mentioned before, where you need to be able to provide, or you need to be able to come out with a table of different kind of atomic absorption spectroscopy. So because here we also have we have come out with the table, but also even though you have this table, but I would, this is for your own good actually. So you, if you be able to add some things to it to make it very compact, because all of this is chapter 3 and chapter 4 actually. All right, so in terms of any questions, we would be able to have the discussion on Thursday. Okay. All right, so feel free to jot down any questions or any query that you need clarifications on. So we will discuss it on next Thursday. All right, thank you everyone.